This chapter is about building control over haloalkanes and haloarenes, not just remembering reactions, but understanding how naming, bonding, and preparation connect. We'll move through three layers: how to name them correctly, how the CX bond behaves, and how these compounds are actually prepared. Once these three are clear, most questions stop feeling random. Keep the roadmap very clear in your head. First comes nomenclature. If the name is wrong, everything built on top of it collapses. Then comes the nature of the CX bond. This is where polarity and reactivity come from. After that, preparation methods. And this is where most exam questions are framed. And finally, name reactions. These are just compact applications of everything before. Think of it as a sequence, not four separate topics. When it comes to nomenclature, the biggest mistake students make is trying to read the structure as it is drawn. That doesn't work. Start by identifying the root chain or ring. Number it properly. Only then start attaching substituents. If it's a benzene ring, draw and number the ring first. Then place substituents. One place where students lose easy marks: sec-butyl. It gets confused with isobutyl all the time. Examiners know this, so they test it. So the rule is simple: root numbering substituents. Never reverse this order. The moment a halogen attaches to carbon, the bond stops being neutral. Halogens are highly electronegative. They pull electron density toward themselves. So carbon becomes partially positive and the halogen becomes partially negative. That makes the bond polar. And that polarity is not just a property, it explains reactivity. The carbon becomes the target for nucleophiles. If you remember one thing here, the CX bond creates a reactive site. Now look at how the bond behaves across different halogens. As you go from fluorine to iodine, bond length increases and bond strength decreases. That part is expected. But dipole moment is where most students go wrong. You would expect CH3F to have the highest dipole moment because fluorine is most electronegative. It doesn't. CH3Cl actually has a higher dipole moment than CH3F. Why? Because bond length also plays a role. This is where most aspirants lose marks. They rely only on electronegativity and ignore structure.
When it comes to preparation, don't think in terms of reactions. Think in terms of pathways. There are three main routes: from alcohols, from hydrocarbons, and through halogen exchange. Every method you study will fall into one of these. That simplifies the entire chapter.
Take alcohols first, and within that, the most reliable method using thionyl chloride. Alcohol reacts with SOCl2 to give alkyl fluoride, along with SO2 and HCl as gases. And that detail is the key. Because the byproducts escape as gases, the reaction moves forward cleanly and leaves behind a pure product. In MCQs, this method is usually the safest choice when purity is mentioned. Alcohols can also react using HX or phosphorus halides. With HX, reactivity follows a clear order. Tertiary alcohols react fastest, then secondary, then primary. ZnCl2 is used to help 1 degree and 2 degree alcohols react. Then come phosphorus reagents, PBr3, Pi3, and PCl5. A detail worth locking in: PBr3 and Pi3 are unstable. They are generated inside the reaction mixture itself. That's the kind of line examiners turn into a direct question.
Here's where the pattern breaks, aryl halides. If you try to apply the same alcohol-based methods to phenols, they fail. Because in phenol, The CO bond is strengthened by resonance with the benzene ring. It gains partial double bond character, so it becomes much harder to break. This is why HX, PX3, and SOCl2 don't work here. If you miss this exception, you'll misapply the entire preparation logic.
From alkanes, the method is free radical halogenation. And this is where students often make a wrong assumption. Yes, it works, but it produces a mixture, multiple isomers, multiple substitutions. It is messy. So if a question asks for a single pure product, this method is almost always the wrong choice.
From alkenes, things are much more controlled. Hydrogen halides add across the double bond, and the product is decided by Markovnikov's rule. The halogen goes to the carbon with fewer hydrogen atoms, so the more substituted carbon gets the halogen. If you ignore this orientation rule, you'll get the product wrong even if you know the reaction.
There's also a simple lab test linked to alkenes. Bromine in carbon tetrachloride is reddish-brown. Add an alkene, and the color disappears as a Victi bromide forms. That color change is the signal for unsaturation. It's a small detail, but it appears regularly in objective questions. Now come to halogen exchange reactions. The first is the Finkelstein reaction. An alkyl chloride or bromide reacts with NaI in dry acetone to give an alkyl iodide. The important part is not just the substitution, it's what happens to the byproduct. NaCl or NaBr precipitates out. That removal pushes the reaction forward. So this is not just a reaction, it's equilibrium control. The second exchange method is the Schwarz reaction. This is used to prepare alkyl fluorides, which are otherwise difficult to synthesize directly. The reaction uses metallic fluorides like AgF, Hg2F2, COF2, or SbF3. If you see these heavy metal fluorides in a question, the answer should come instantly. Schwarz reaction. That recognition saves time. Bring everything together. From alcohols, you have SOCl2 as the cleanest route, along with HX and phosphorus reagents. From hydrocarbons, alkanes give messy mixtures, while alkenes give controlled addition products. From halogen exchange, Finkelstein gives iodides and Schwarz gives fluorides. Here's a summarized flowchart of all preparation methods from memory. Start from alcohols, hydrocarbons, and halogen exchange and connect them to the final products. Now, if you can reconstruct that flow without looking, you're not memorizing anymore. You understand the chapter.
This chapter is not about memorizing random formulas.
It is about learning to identify haloalkanes. Halogenated compounds appear in medicine and chemistry all around us. Chloramphenicol is linked with typhoid, chloroquine with malaria, thyroxine with goiter, and halothane with surgery as an anesthetic. Fluorinated compounds also show up in blood substitutes and inhalation-related applications. So this chapter is not abstract chemistry. It connects directly with health and industry. Here's a trap you need to be aware of. Halogenated compounds are often highly stable, which is why they can persist and resist breakdown in the environment. Classification begins with a simple two-step filter. First, count how many halogens are present: mono, di, or poly. Then check what kind of carbon the halogen is attached to. If it is attached to an sp3 carbon, you are dealing with a haloalkane. If it is attached to an sp2 carbon, the compound falls into the haloarine or vinylic category. That classification logic matters because naming and reaction behavior both depend on it. The safest habit is to identify the type before trying to solve anything else. Haloalkanes are the simpler branch to understand because the halogen sits on a saturated carbon chain. That carbon may be primary, secondary, or tertiary depending on how many neighboring carbons it is attached to. Allylic and benzylic halides also belong here because the halogen is still on an sp3 carbon, even though the carbon is next to a double bond or attached to an aromatic ring. Here's the important distinction. The carbon carrying the halogen is still sp3, so the compound behaves like a haloalkane in classification terms. Haloarenes and vinylic halides behave differently because the halogen is directly attached to an sp2 carbon. In vinylic halides, the carbon is part of a C-C double bond. In aryl halides, it is part of an aromatic ring. That direct attachment changes the bond character and makes them less reactive than ordinary alkyl halides in many cases. Here's a trap you need to be aware of. There is no buffer carbon here. The halogen is sitting directly on the active site, so you cannot treat these compounds like normal haloalkanes. The difference between allylic and vinylic halides is one of the easiest places to lose marks. In allylic halides, the halogen is on the carbon next to the double bond. That carbon is still sp3 hybridized. In vinylic halides, the halogen is directly on the double bond carbon itself, which is sp2 hybridized. That small shift changes everything. If you can't spot whether the halogen is on the double bond or beside it, the rest of the question becomes a guess. Geminal and vicinal dihalides are really about neighborhood. If both halogens sit on the same carbon, it is geminal. If they sit on adjacent carbons, it is vicinal. The memory trick is simple. Geminal means twins. Vicinal means neighbors. That naming logic is important because it shows up in both classification and reaction products. Once the positions are clear, the name becomes automatic.
A named example makes the rule concrete. In the structure shown here, the correct IUPAC name is 1-bromo-2-pot-2-dimethylpropane. Notice the systematic way it is built. First choose the root chain, then number it, then place the substituents. Common naming can sometimes be misleading, but IUPAC demands exact numbering. Here's a trap you need to be aware of. Do not start from the halogen and guess the name casually. Build the parent chain first, then attach the branches.
For a formula like C5H11Br, systematic thinking beats guessing. You first look at the possible carbon skeletons, then place the halogen in all non-equivalent positions. That is why the isomer count is organized by primary, secondary, and tertiary carbon arrangements. The method matters more than the final list. If you try to brute force it, you will miss isomers or count duplicates. The smart approach is to lock one carbon position, then move the branches carefully.
The CX bond is where reactivity begins. Halogens are highly electronegative, so they pull electron density toward themselves. That leaves carbon partially positive and halogen partially negative. So the bond is polar, and that polarity is the reason haloalkanes become such useful substrates in substitution reactions. If you understand this, nucleophilic attack stops looking like memorized chemistry and starts looking like an obvious consequence of charge distribution.
Haloalkanes become such useful substrates in substitution reactions.
If you understand this, nucleophilic attack stops looking like memorized chemistry and starts looking like an obvious consequence of charge distribution.
The bond properties follow a predictable sequence. As halogen size increases down the group, bond length increases and bond enthalpy decreases. A longer bond is easier to break, so Ci is weaker and more reactive than Cf. The interesting part is dipole moment. It does not simply follow electronegativity alone. This shows that CH3Cl has a higher dipole moment than CH3F because bond length also contributes. Here's a trap you need to be aware of. Do not rely only on electronegativity when comparing dipole moments. Bond length matters too.
The preparation logic starts from one simple observation. The carbon in haloalkanes is electron deficient, so it is a perfect target for nucleophilic substitution. That is why alcohols are such an important starting material. They are accessible and they convert efficiently into alkyl halides. This is the cleanest bridge from a common functional group to haloalkanes. Why alcohol-based preparation appears first in the chapter.
We hope that you have understood the topic. For more such content, explore EduRev app.